Hello everyone. Are you okay? I hope so. I will present our work entitled Topography Food Strategy Applied to Real-Time Motion Capture Data using Kinect Sensor. My name is Danilo. I am a Brazilian researcher and assistant professor at State University of Piauí. The other part of this work and I are part of the research group CRAB on computer graphics, virtual reality, and animation at the Federal University of Ceará. The question we try to answer in this work is it possible to obtain good interactive physics-based animations using a low-cost capture sensor in real time? The basic idea is to get a movement captured using Kinect, process this movement in a physical environment to obtain animations compatible with the real world. The steps to obtain those animations are as follows. First, we must have an excellent physical environment that makes possible physically realistic interactions with appropriate collision treatment. For this, we use a physics engine called ODE, Open Dynamics Engine, that is widely used in this field. Second, we should have a good balance strategy that ensures good postures of the simulated character. When we work with physical environment, we are interacting with diverse forces in an articulated character. For this interaction to work as we hope, we use controllers that cooperate for a good balance. In this work, we use a controller that is very robust, fast, and handles easily characters with simple geometry. Lastly, our data is captured directly using a low-cost sensor, the Microsoft Kinect. Like other capture sensors, Kinect has noise problems. Noise problems include undetected positions, misorientations of some joints, or both. To minimize those problems, we did some process on the data at runtime. We treat the joint's angular limitation to reduce the range of possible angles, and previous orientations are used if we do not get these orientations of the joint. So, our controller graphical abstract is represented in this image. As input, we take the position and orientation data of the joint captured by Kinect in each instant of time. This data goes in your simulated character. We apply some controllers to track the movement and keep the balance, reacting to the simulation's support chains. These support chains are considered an Achilles tendon when performed in a simulated environment. We'll show how to work to implement this support policy. Next, we'll talk about each part of the movement control. Tracking. The proportional derivative control is used to reach the character's joint angles given by Kinect in each instant of time. We used two open source packages to get the Kinect data, OpenKinect Project and OpenNI. However, some data we are not able to obtain. For example, in the red markings, we find problems getting data related to the position and or orientation. Although we have those limitations, the motion controllers has not been prevented from achieving the goals. Balance. Our balance controller uses virtual actuators to push the center of mass to a desired position, which we call the balance position. calculated based on the support foot data. This control also rotates the chest to the desired orientation to get a good posture. This controller is based on a Jacobian matrix. Our contact exchange policy, the supervisor, combines the information from the simulated environment's foot and the position data to assign the support fit to the balance control. So, how does this policy work in our simulation? Using Kinect, we only have the position information of the foot to assume a support configuration. Therefore, we can take into account the initial data captured by Kinect. When the person goes to the front of the Kinect, we get the foot's initial position. Assuming a virtual error in this capture, we define an acceptable error for the foot's height about its initial position that will be checked at each instant of time to determine whether the foot is on the ground or in the swing phase. At this point, the simulation support policy checks the character's foot contact on the ground and the center of mass projection. We say that the character is in a dual stance or single stance based on the projection of the center of mass and the support zones, represented by the circle in green.
The area.
Of this support zone is defined by the user. For example, in the single stance, when the center of mass is over a single zone, we will take only one foot to provide the support. When the center of mass is over two zones or in none, we say that the character is in dual stance. Using this approach, when the person raises a leg, the simulated character is expected to perform the same movement. Besides, we work with Symbicon's strategy to move the leg that is in swing phase. This strategy is based on the center of mass speed to increase the leg's range of motion. Without using this approach, the leg stayed very close during the switching from swinging leg to stance leg. Lastly, to make the character as stable as possible, we use an approach called the double free foot, without slipping quickly and falling. In this approach, we have an external force applied to the foot that simulates a more robust or larger foot. This makes our character better adapt to support chains and interactivity without worrying that it will fall to the ground. More details of those two approaches can be found in our previous work. The new contributions are mainly related to tracking and contact exchange policies, where we get some exciting results. Here is an overview of one of the tests that we did with user interactivity. In A, we have the simulated character. We can see in B the skeleton of the person captured by the Kinect. Next, in C, we have the TFF, Double Free Foot approach. Here, we determine when the foot should remain firm. The smaller this area in purple, the more unstable it becomes. In D, we have the user's first-person view. Last, in E, we can control the angular limits at the joints of the character. In this first result, we show real-time interactivity. In this case, The user must prevent the balls from falling. Here, one can see that some joint angles are not captured perfectly by Kinect. Although this happens, our strategy has adapted well to the movement and showed a good result. In this comparative animation, we can observe the angular limitation being applied. Note, for example, the knee angle limitation, so that it does not bend too much. Here, we show the support strategies being applied. In this first animation, we show only the Kinect strategy being applied. In the second, we add the strategy based on the simulation, based on the center of mass over the support zone. In this last example of the support change, we show the combination of both previous strategies together with Simbicon. In the following animations, we adopt the three strategies combined. This boot character is a default model that we have adopted. We will show other morphologies where contact changes flow more naturally when adapted to the user. To make the results more realistic, we made our character adapt to the user morphology. For that, we investigated two possibilities. Use morphologic proportion, in which, based on the user height, we define the dimensions of the leg, arm, etc. Another approach is to build the limbs dimensions according to the extractions of joints positions kept by Kinect. It was observed that the approach using Kinect produced a smaller character than using anthropomorphic proportions. We will show a comparison using these two approaches. Here we have a 1.66 meters volunteer. Here we have a volunteer with 1.86 meters. Note that using a morphological approach with Kinect, the movement was much smoother. Finally, we add the choice of which animation policy we want to emphasize, the balance or posture. So, if I want to emphasize the balance, I want his center of mass to be in the support zone, even though it neglects the Kinect movement, and vice versa. If I want to focus on posture, I give up the naturally correct balance. That is what we have shown in this last example. At the top, we determine where the focus is, whether in posture or balance. See that the center of mass can quickly go to the support region's limit when the focus on the pulse. In this example, we apply an external force to the pelvis to put it back, and we change the focus. When I change to emphasize balance, the arms remain more in a position where the center of mass goes to the desired position of support, rather than the pulse. Okay, here are the conclusions and future work. We present a physical simulation in real time using Kinect, and even with some difficulties in contact chains, we have achieved good results. In future work, we hope to improve our support supervisors' skills to make it possible for us to work with high energy movements, such as jumping and running. Thank you for your attendance.